Welcome to this video, where we take a look at techniques for solving cubic equations for A-level mathematics. But first of all, let's have a look at what we mean by the terms cubic expression, function and equation, because these terms refer to different but related things, and we need to be clear about what we mean when we talk about, say, a cubic equation. In what follows, the coefficients a, b, c and d will be assumed to be real constants, and a is not equal to 0. A cubic expression is an expression which can be written in the form ax cubed plus bx squared plus cx plus d, where x is a variable and so different values of x will result in different values of the expression. A cubic function is a function which can be written in the form f of x equals ax cubed plus bx squared plus cx plus d, where again x is a variable and different values of the variable will correspond to different values of the function. Of course, it's common to use another dependent variable y instead of f of x, and so different values of x will give rise to different values of y. A cubic equation is an equation which can be written in the form ax cubed plus bx squared plus cx plus d equals 0, and in this case x is not a variable but can be any value which satisfies the equation. Each of the values of x for which the equation is satisfied is called a solution, or sometimes a root of the equation. Every cubic equation has at least one real solution, but may have more. Note that in each of these I say can be written in the form. An equation such as, say, x cubed plus 2x equals 4 plus 5x squared is still a cubic equation, but it's not in the form ax cubed plus bx squared plus cx plus d equals 0. Nevertheless, this equation can be brought into the form ax cubed plus bx squared plus cx plus d equals 0. In this video, I won't be looking at cubic functions, nor will I be showing how to sketch the graphs of cubic functions. I'll cover that stuff in another video, and in this video I'm just going to concentrate on cubic equations. A cubic equation can have various different combinations of solutions, such as one real solution and two complex solutions, a double repeated real solution and another real solution, a triple repeated real solution, or even three distinct real solutions. In this video, except for maybe the extra stuff section, we'll only be concerned with cubic equations with real coefficients and real solutions. At A level, there's only really one way to solve cubic equations, and that's through factorization and application of the factor theorem to obtain a suitable factorization. Therefore, to solve the cubic equation ax cubed plus bx squared plus cx plus d equals 0, actually, do you know what, let's divide through by a to make things a bit simpler, and we can do this since a is not equal to 0, so to solve the equivalent equation x cubed plus b over a x squared plus c over a x plus d over a equals 0, we look for numbers p, q and r so that x minus p times x minus q times x minus r is identically equal to x cubed plus b over a x squared plus and so on. And so the solutions to the equation x cubed plus b over ax squared plus and so on, and therefore also the solutions to the equation ax cubed plus bx squared plus cx plus d equals 0 will be x equals p, x equals q and x equals r, where some or all of p, q and r may be equal. In the case where the cubic equation has only a single real solution, then we can't obtain a full factorization of the cubic, at least as far as we're concerned in this video. So we can only obtain a partial factorization, such as x minus p times qx is identically equal to x cubed plus b over ax squared plus and so on, where qx is a quadratic with no real roots, and in which case the only real solution to the cubic equation is x equals p. So let's have a look at a couple of simple examples of solving cubic equations by factorization. Find all solutions of the cubic equation 8x cubed plus 2x squared minus 3x equals 0. So this is an easy one because there's no constant term, so this is only slightly more difficult than solving a quadratic equation. Since there's no constant term, just take x out as a common factor to give x times 8x squared plus 2x minus 3 equals 0, and then factorise the quadratic inside the brackets to give x times 4x plus 3 times 2x minus 1 equals 0, And so the solutions are x equals 0, x equals minus 4/3, and x equals a half. Easy peasy. Find all solutions to the equation as shown on the screen. Of course, this is not a cubic equation. Nevertheless, some equations can be brought into the form of a cubic equation and solved as if they were cubic equations. So, assuming that x is not going to be equal to any values which will make either of the denominators equal to 0, and if that is the case, then we'll cross that bridge when we come to it, then let's multiply both sides by 3x times 2x cubed plus x plus 12 to give 2x cubed plus x plus 12 equals 3x times x plus 8. And now, everything's straightforward. Expand brackets to give 2x cubed plus x plus 12 equals 3x squared plus 24x. And so 2x cubed minus 3x squared minus 23x plus 12 is equal to 0. And it's factor theorem time. So let p of x equal 2x cubed minus 3x squared minus 23x plus 12. Then p of 1 is equal to minus 12. P of 2 is equal to minus 30. And continuing on in a suitably systematic way, it turns out that p of 4 is equal to 0. And so by the factor theorem, x minus 4 is a factor. So p of x is equal to x minus 4 times q of x, where q of x is a quadratic, equal to ax squared plus bx plus c. So therefore, p of x is equal to x minus 4 times 2x squared plus bx minus 3. And so I can see that b must be equal to 5. So p of x is equal to x minus 4 times 2x squared plus 5x minus 3. And therefore p of x is equal to x minus 4 times 2x minus 1 times x plus 3. And the solutions to the equation px equals 0 are x equals 4, x equals a half, and x equals minus 3. Now, do any of these values of x make the denominators of the original equation equal to 0? No. So in that case, all of these values of x are also solutions to the original equation. Remember that the cubic equation that we've just solved here is not the original equation that we wanted to solve. So for example, suppose I wanted to solve the equation x squared plus 3x minus 4 over x squared plus 7x plus 12 equals 0. Then I might multiply through by x squared plus 7x plus 12 to get x squared plus 3x minus 4 equals 0. And then solve this quadratic to get x equals minus 4 or x equals 1. Job done, right? Well, unfortunately not, because the quadratic equation that I've solved is not the equation that I originally set out to solve. It turns out that if x equals minus 4, then x squared plus 7x plus 12 equals 0. In other words, the denominator of the original equation is equal to 0 for this value of x. And in other words, although x equals minus 4 is the solution of the quadratic equation x squared plus 3x minus 4 equals 0, it's not a solution of x squared plus 3x minus 4 over x squared plus 7x plus 12 equals 0. And you must always bear in mind that although you can change the form of an equation to something easier to solve, the new equation that you solve is not the same equation as the one that you started with. The new equation is just something that you're using because some, possibly all, of the solutions to the new equation coincide with the solutions to the original equation, but it's up to you to check this. So now let's have a look at some more complicated examples. As ever, there's the usual disclaimer here that I make no suggestion that the problems that I present are exam style, nor that the solutions to the problems that I present are the best solutions or the way of solving the problems. The solutions that I present are just my solutions to these particular problems. On another occasion, I may choose a different approach to solving the problems, but today I've gone for these solutions. Generally speaking, I'm not concerned with problems being exam-style problems. I'm more interested in helping people to just develop their problem-solving skills through solving sufficiently challenging and interesting problems. So here we go. Use factorization to find all solutions to the equation 6x cubed minus 5x squared minus 17x plus 6 equals 0. And we don't really have much of a choice here about which way to go. We're going to have to use the factor theorem to try to find a factor. So as ever, when using the factor theorem, we look for numbers a such that p of a is equal to 0, where in this case we set p of x equal to 6x cubed minus 5x squared minus 17x plus 6. Just be systematic. Let's try p of 1, which turns out to be minus 10. P of minus 1 is equal to 12, P of 2 is equal to 0, and so x minus 2 is a factor by the factor theorem. So P of x is equal to x minus 2 times q of x, where q of x is some quadratic polynomial. This can be obtained using algebraic long division, but because I typically try to avoid using algebraic long division unless I really have to use it, then I'm not going to bother with it here. That's not to say that there's anything wrong with the technique or that I'm suggesting that you shouldn't use it. I'm just stating a personal preference. So if q of x is equal to ax squared plus bx plus c, then it must be that a is equal to 6 and c is equal to minus 3. How do I know? I'm considering what I would get if I expanded out the expression x minus 2 times ax squared plus bx plus c. In particular, I know that I would get a term ax cubed and a term minus 2c. And since this must be identically equal to 6x cubed minus 5x squared minus 17x plus 6, then ax cubed must be equal to 6x cubed, and so a is equal to 6, and minus 2c must be equal to 6, giving c equals minus 3. Note that I'm not just expanding the brackets out completely, I'm being more selective about things so that I don't create unnecessary work where I don't have to. So we have P of x is equal to x minus 2 times 6x squared plus bx minus 3. So now considering the sum of the x squared terms that I would obtain from expanding out, I'd get the coefficient of x squared to be b minus 12, and so b minus 12 is equal to minus 5, giving b is equal to 7. So P of x is equal to x minus 2 times 6x squared plus 7x minus 3. So now simply factorise the quadratic expression to give P of x is equal to x minus 2 times 2x plus 3 times 3x minus 1. And so the solutions to the equation P of x equals 0 are x equals 2, x equals minus 3 halves, and x equals a third respectively. Of course, if you were lucky enough to try out the values minus 3 halves and or 1/3, you would find that P of minus 3 halves and P of a third are both equal to 0, in which case you could apply the factor theorem to them. But let's face it, who's going to try those values? Given that P of x is equal to 3x cubed plus k minus 6x squared plus 2 times 1 minus kx minus 4, and x is equal to 2, is the only real solution to the equation P of x equals 0, find the possible values of k. Since x equals 2 is a solution to the equation P of x equals 0, then P of 2 equals 0, and so x minus 2 is a factor of P of x by the factor theorem. So P of x can be factorised as P of x equals x minus 2 times q of x, where q of x is equal to ax squared plus bx plus c, and it's clear that a is equal to 3 and c is equal to 2. And so P of x is equal to x minus 2 times 3x squared plus bx plus 2, and it's also easy to see that when expanded out, the coefficient of the x squared term will be b minus 6, and the coefficient of the x term will be 2 minus 2b, and so b must be equal to k, giving P of x is equal to x minus 2 times 3x squared plus kx plus 2. And since 3x squared plus kx plus 2 has no real roots, then its discriminant must be less than 0. So k squared minus 4 times 3 times 2 is less than 0. And the solution set to this quadratic inequality is minus the square root of 24 is less than k, less than the square root of 24. Of course, the surds need to be simplified to give minus 2 root 6, less than k, less than 2 root 6. When it comes to using the factor theorem at A level, then you can be fairly certain that there will be a factor corresponding to some small valued integer, probably somewhere between and including minus 3 and 3. And this can be easily found using the factor theorem. Just be systematic in your search for a factor. There's no shortcut, just get on with it. And you may ask, what about those cubics which don't have nice factors, which might come up outside of A-level maths? In theory, the factor theorem still applies, but in practice is not necessarily going to be terribly effective. At A-level, this is not going to be a problem for you. Of course, this is a problem once you consider cubics that are not as well thought out as those meant for A-level maths exams. In this case, potentially other more practically effective or more sophisticated techniques may be required to find the factors. Unfortunately, there's no easy way, and in fact probably no way at all, to determine just by looking at a cubic whether it's going to be straightforward or not to find a factor using the factor theorem. That's just one of the hurdles that you'll have to deal with if and when you consider more complicated cubics. As with any other problem, you just have to be prepared to use whatever techniques you have available to you to solve the problem. That is, of course, if you are sincere about solving the problem in the first place. So here we come to the extra stuff part of the video. In this part of the video, A-level maths specifications go out of the window, and I just look at whatever aspects of mathematics I feel like looking at. On that note, you shouldn't expect to be examined on much of the stuff that I talk about in this section of the video. In fact, I don't think there's anything that you would be examined on at all. Of course, just because something isn't examinable doesn't mean that it's not worth knowing. I know, crazy, right? So stick around if you want to see mathematics from a different perspective. If you don't, then I have some other A-level maths tutorial videos on my channel which may interest you instead. I mentioned earlier in the video that every cubic equation has at least one real solution. Here's Leonhard Euler's proof that every polynomial of odd degree has at least one real root, which of course includes cubics, which are polynomials of degree 3. The translation from Latin is my own. Like quadratic equations, the solutions to cubic equations have been considered for many centuries, right back to Babylonian times, though in comparison with quadratic and certainly linear equations, there are relatively few instances of cubic equations being mentioned or solved. Even when cubic equations are being considered, they often do not take forms that are easily recognisable as cubic equations to a modern reader. In Thomas Heath's introduction to the works of Archimedes, we read, "The question arises, did the Greek geometers deal thus generally with the cubic equation x cubed plus minus ax squared plus minus bx plus minus gamma equals 0? Which, on the supposition that it was regarded as an independent problem in solid geometry, would be for them a simple equation between solid figures, x and a, both representing linear magnitudes, b an area, a rectangle, and gamma, a volume, a parallelepiped." Also in the introduction, we read, "There can be no doubt that Archimedes solved this equation, x cubed times 3a plus x equals b squared c, as well as the similar one with a negative sign, i.e. he solved the two equations x cubed plus minus ax squared minus plus b squared c equals 0, obtaining all their positive real roots. In other words, he solved completely, so far as the real roots are concerned, a cubic equation in which the term in x is absent, although the determination of the positive and negative roots of one and the same equation meant for him two separate problems." When Heath says that Archimedes solved these equations, that's not to suggest that Archimedes wrote these equations in the forms that we're familiar with. What Heath means is that the problems that Archimedes solved are in many ways comparable with or equivalent to the algebraic equations that we often write in modern mathematics. The algebraic notation that we use to represent cubic equations didn't exist in Archimedes' time. We also read in Heath's translation of Diophantus of Alexandria's Arithmetica, "There is no ground for supposing that Diophantus was acquainted with the algebraical solution of a cubic equation. It's true that there is one cubic equation to be found in the Arithmetica, but it's only a very particular case. In 6.17, the problem leads to the equation x squared plus 2x plus 3 equals x cubed plus 3x minus 3x squared minus 1. And Diophantus says simply, whence x is found to be 4. He goes on further to say, "It's not possible to judge from this example how far Diophantus was acquainted with the solution of equations of a degree higher than the second." And we read in Mario Livio's book, The Equation That Couldn't Be Solved, the ancient Babylonians did generate some tables that allowed them to solve a very few specific cubics, and the Persian poet-mathematician Omar Khayyam presented a geometric solution to a few more in the 12th century. However, the solution to the general cubic equation defied mathematicians until the 16th century. Staying with Omar Khayyam, then in Julian Lowell Coolidge's book, The Mathematics of Great Amateurs, 2nd edition, we read, "Omar's fame as a mathematician rests chiefly on his claim to be the first to handle every type of cubic that has a positive root. Coolidge gives some examples of typical problems that Omar solved, such as problem 1. A cube, some sides and some numbers are equal to some squares, which corresponds to the equation x cubed plus b squared x plus a cubed equals cx squared. Problem 2. A cube and some squares are equal to some sides and a number, which corresponds to the equation x cubed plus cx squared equals b squared x plus a cubed. And problem 3. A cube and some numbers are equal to some squares and some sides, which is the equation x cubed plus a cubed equals cx squared plus b squared x. Omar solves these problems geometrically, and Coolidge gives examples in his book of typical solutions to these problems, albeit using more modern notation. So now let's have a look at the general cubic equation which defied mathematicians for so long. The analogue to the quadratic formula is the cubic formula, which is not at all as straightforward to use as the quadratic formula, and it's no surprise that the cubic formula is not given as a possible method of solving cubic equations at A level. The solutions to the cubic equation x cubed plus px plus q equals 0 are given by the three formulae shown on the screen, where j is equal to e to the power of 2 pi I over 3, or minus a half plus I root 3 over 2, where I is equal to the square root of minus 1. And it may be that all three roots are real, so even though the second and third formulae involve complex numbers, this doesn't imply that the values of x are also complex or imaginary numbers. I was going to give a derivation of these formulae in this video, but I've decided against it so that the video remains a reasonable length. Nevertheless, it isn't difficult to find a derivation of these formulae on the internet. We read in The History of Mathematics, a Reader, edited by John Forville and Jeremy Gray, the first person to solve cubic equations algebraically was Scipione del Ferro, who was Professor of Mathematics at Bologna. This is not to suggest that Del Ferro was the one who first discovered the formula that I've given previously. In modern mathematics, we're able to consider all cubic equations as being of a single form, ax cubed plus bx squared plus cx plus d equals 0, where the coefficients can be positive or negative or whatever. However, in the past, only positive coefficients were considered, and so there was a multitude of different forms that cubic equations could take. We read in Carl Boyer's A History of Mathematics. Today we think of cubics as all essentially of one type and as amenable to a single unified method of solution. At that time, however, when negative coefficients were virtually unused, there were as many types of cubics as there are possibilities in positive or negative signs for coefficients. Therefore, different formulae, each similar in nature to the one given earlier in the video, would have to be derived for each type of cubic equation, and it may be that mathematicians at the time were able to solve some types of cubic but not others, as Antonio Fior discovered to his dismay during his cubic solving challenge with Niccolò Tartaglia. Each man presented the other with 30 cubic equations to be solved. Tartaglia utterly trounced Fior by solving all 30 equations that Fior set for him within a day. Fior managed to solve none of those that Tartaglia set. Evidently, Tartaglia was in possession of formulae for solving a much greater range of types of cubic equations than Fior. Tartaglia was able to solve 3 types of cubic equation, and to ensure that he could remember the different methods or formulae required for the solution to each type, he put the methods into verse. Tartaglia's verses can be seen in Appendix 5 of Mario Livio's book, The Equation That Couldn't Be Solved. The formula for solving a cubic equation opened a new can of worms, as we read in Boyer. Whenever the 3 roots of a cubic equation are real and different from 0, the Cardan-Tartaglia formula leads inevitably to square roots of negative numbers. The goal was known to be a real number, but it could not be reached without understanding something about imaginary numbers. The imaginary now had to be reckoned with, even if one did agree to restrict oneself to real roots. Just as there is a discriminant of a quadratic equation, and the discriminant of the quadratic equation ax squared plus bx plus c equals 0 is of course b squared minus 4ac, there's also a discriminant for cubic equations. However, since any cubic equation ax cubed plus bx squared plus cx plus d equals 0 can be brought into the form y cubed plus py plus q equals 0 via the transformation x equals y minus b over 3a, then we only need to consider the discriminant of cubic equations of this latter form. The discriminant of a cubic equation of the form y cubed plus py plus q equals 0 is given by the expression minus 4p cubed minus 27q squared. and I won't explain in this video where this expression comes from because it would take far too long. However, this expression, or something very closely related to it, appears in the cubic formula. There's a discriminant for the cubic equation ax cubed plus bx squared plus cx plus d equals 0, which is a more complicated expression, but since any cubic can be expressed in this reduced form, then we can get away with just considering the discriminant of the reduced form. The discriminant of a polynomial can tell us certain information about the roots of that polynomial. For quadratic equations, it's well known what it means for the discriminant to be greater than, equal to, or less than 0, so I won't repeat that here. But for example, if the discriminant of this cubic is equal to 0, then it's clear that there must be a double repeated root, which may be real or not. If the discriminant is greater than 0, then there will be 3 real roots. If the discriminant is less than 0, then there will be 1 real root and 2 complex conjugate roots. Furthermore, much of what we've seen so far about cubic equations extends to quartic equations. That is, equations which can be written in the form ax to the power of 4 plus bx cubed plus cx squared plus dx plus e equals 0, where of course a is not equal to 0. There's a discriminant corresponding to this type of equation, and there's a quartic formula, neither of which I'll state here. The quartic formula is massive, by the way. However, that's where things end for us. For the general quintic, degree 5 equation and above, there is no formula, which only uses the algebraic operations of addition, subtraction, multiplication, division, raising to a power, and extraction of roots, which can be generally applied to obtain the solutions. This doesn't mean that there are no techniques for solving such equations, and it certainly doesn't mean that these equations have no solutions. There are various techniques that can be applied, but no single formula which works for all cases. This also doesn't mean that such a formula just hasn't been found yet, or that the formula is just too complicated. Complicated formulae are no deterrent for mathematicians. It can be proved that no such formula exists. So the reason one hasn't been found is because there isn't one to find. And the heroes of the history of solutions of polynomial equations are arguably Niels Henrik Abel and Évariste Galois. I won't go into detail about their lives and discoveries here, but Mario Livio's book, which I've mentioned previously, The Equation That Couldn't Be Solved, is a very interesting and accessible account of the history of attempts to find the solutions to polynomial equations, and gives plenty of details of Abel's and Galois' lives. I highly recommend reading this book if you want to get a bit more of an idea of the history of solutions to polynomial equations. So here we are once again at the end of another video. Thank you for watching right to the very end, and I hope that you found something useful and or interesting amongst my many ramblings. Please remember to subscribe to the channel and hit the like button to show your support. If you have any questions about anything that I've mentioned in this video, then please get in touch or leave a comment in the comments section. More videos will be gradually uploaded to this channel as often as I can make them. If you have any ideas about anything maths related that you'd like me to make a video on, then please let me know. That's all, folks.